Next, we're going to take a look at the conditions for inference. What I will say before I go over this is that conditions for inference do look confusing, but most of the time, the conditions for inference for a test on the slope will be already given to you. So even though I'm going over them, you almost never will have to actually do all of the conditions. Okay, so number one, in order to perform inference on a linear regression model, there's detailed conditions which must be met, which is why they'll almost always be given to you. The regression model requires that for each possible value of the explanatory variable x, the following have to be true. Number one, the mean value of the response variable falls on the population regression line of the mean of y is equal to a plus bx. So that's basically just saying that the mean of y is on the line. And remember, we already talked about in our previous modules that, or our previous lessons, that the mean of x and the mean of y were on the regression line. This is just like saying that the mean of y, the population mean of y, and the population mean of x are on your regression line. The second one is, and this is the one that's a little bit confusing, the values of the response variable y follow a normal distribution with a common standard deviation. This is the explanation from the first bullet point on the previous page. All possible y values for one x value when plotted from a normal distribution. Okay, so that's confusing. So basically all that means is if I have an x value right here, the x value, remember, that is what you are starting with. You're picking one x value. But remember, okay, remember that your y value is going to change based on your regression line. So every time you take a sample, the slope is going to change. So it's just like saying for every x value, your y values are going to form a normal distribution. So this is like saying this would be y is 1, this is y is 2, 3, 3, 3, 3, 3, 4, 4, 4, 4, 5, 6, 7. So notice they're clustered around 3 and 4, okay? And then that's just showing that these are all of my possible response variables y. They have a normal distribution for every single solitary possible x value, okay? So for any fixed x, this is my fixed x, when I pick an x, the responses y follow a normal standard deviation. So, and basically, like I said, every time, if you notice, here's 3 different slopes. Okay, every time you find a new regression equation, the slope's going to change slightly, and therefore the y value is going to change slightly. Now, your assumptions and conditions for your regression equation are going to be longer. There's linear, and that's how you're going to remember them. So there's 1, 2, 3, 4, 5, 6 conditions. However, like I said, I'm going to explain them, but most of the time they'll actually be given to you. They'll say the conditions are met, so you won't necessarily have to give them, but you might have to answer some multiple choice questions about them. Okay, so let's take a look at what they mean. So like I said, you're going to use an acronym linear in order to help you remember the assumptions and conditions. So the L, that's pretty self-explanatory. It means that the relationship between x and y is linear, and you can tell that from a graph. Okay, independent, so same condition from before. The y responses are independent of each other. So basically that's saying when you're sampling without replacement, so I'm taking 20 samples out of the 220, you're going to check the 10% condition, or that the population is more than 10 times the sample size. Now, the normal condition is the one that we talked about on the previous slide. For any fixed value of x, the response variable y varies according to the normal distribution. You can check the residual plot. Is it linear? Most of the time that will be given to you. You will not need to worry about that. This is the other one that we talked about on the previous page. It's a little bit tricky. It's called the equal variance, okay? So the standard deviation of y, which is called sigma, about the true regression line is constant. So basically what that means, when I make a population regression line, and then I take samples, every single solitary one of those samples is going to produce a different line. So for example, if this is my population line, okay, and then these are all of my I took a sample of 20, wrote their equation, sample of 20, wrote the equation, sample of 20, wrote the equation. The standard deviation from this purple line to all of the red lines is exactly the same. Okay, then you're going to take a look at the residuals. The other way you'll be able to tell that is, are the residuals equally scattered above and below the line y equals 0? So if you're checking the residual plot for the normal condition, remember the residual plot, if it's linear, they'll be equally scattered above and below the regression line. That is also going to hold true for your equal variance. The residuals will be equally scattered above and below the line y equals 0. And then you need to make sure that the random condition holds true. The data comes from a well-designed random sample or randomized experiment. Okay, now how can we check those conditions? Like I said, most of the time they're going to be given to you, but you might be asked to check one or two of them. So here, number one, the linear condition, you need to plot the data on a scatter plot. You need to make sure it is actually linear. You can also check the residual plot to make sure the data is randomly scattered about the line y equals 0. So here's your residual plot. Okay, this residual plot says, hey, randomly scattered above and below. So this, we're good to go. It's a linear model. Here, this is a curve. Notice how it goes down and up. So this is not linear. And then here, if we notice, the fan is actually converging together here. Okay, so this is going to tell us that it is not a good linear fit. Now that also helps us with our variance, because notice we kind of have equal distances above and below here. Here, I have unequal distances. I have far distances here above my line and close distances here. Now, independent, so once again, that's going to be the population being 10 times the sample size. For your normal condition, you can make a stem plot, a histogram, or a normal probability plot of the residuals. I would look at the normal probability plot of the residuals to check for skewness and make sure it's approximately normal. Now, that just means, remember, how do we use the normal probability plot? So remember, your normal probability plot of the residuals needs to create a straight line. Now, take a look. We already talked about this. Look at the scatter plot of your residuals here. The vertical spread of the residuals should be about the same to show that they have equal variance. So I have some above, below, these two are about the same, these two are about the same. There should be no fanning or curved pattern to show that the points are not the same distance above and below the line. The random, same condition as before. The data needs to come from a well-designed random experiment, if not, or well-designed random sample. If not, we cannot make inferences about the population. So how do we check the conditions for inference? Start by making a histogram or a normal probability plot of the residuals and also a residual plot, okay? For the linear one, you're going to examine the scatter plot and check to make sure that the overall pattern is linear. So this is your scatter plot. Looked for curved patterns on the residual plot. So your residual plot actually serves two purposes here. One is the linear condition, and then the other is your equal variance. Independent, population 10 times the second sample size. Normal conditions, make sure you're checking the normal probability plot of the residuals, okay, and we're making sure that this is linear. Remember, the normal probability plot is linear. Okay, the plot of the residuals just in and of themselves, not the normal probability plot, is different. Okay, the equal standard deviation, or the variance, is that's going to make sure our residuals are randomly scattered above and below the line y equals 0. If they don't give you the conditions, they'll most likely give you the scatter plot, the normal probability plot of the residuals, and then the graph of the residuals. And just make sure these are different. The normal probability plot of the residuals is different because this is actually the equal standard deviation. That is the residuals plotted against the line y equals 0. So here you're looking for a random scatter, and here you're looking for them to be linear. Okay, and then we just want to make sure that it's a simple random sample. Now, when conditions are met, we can do inference about the regression model. The mean of y is equal to a plus beta x. Okay, so remember, beta is your population slope, population y-intercept and the population average of y. So let's take a look at what our unknown parameters are. Now we can calculate the least squares regression line. We're assuming, just like whenever we did our other tests for inference, that this slope is an unbiased estimator of the population slope. So what does that mean? That means that if it's unbiased, the slope of the sample is going to be close to the slope of the population, or it's not consistently too big or consistently too small. The y-intercept is an unbiased estimator of the population y-intercept alpha. The remaining parameter is the standard deviation. So basically, remember, the standard deviation describes the variability of the response y about the population regression. And I know that sounds confusing, but it's literally just saying, okay, if I have my line, okay, what is this, how far away, okay, what is the variability, what is the average distance, or what's the average that I'm going to be off by when I predict my population? All right, now, since the population standard deviation is going to be unknown, we're going to use, check a look at this. Okay, we've already talked about this, the standard deviation of the line to estimate the value of the standard deviation of the population of y. Now, let's think about the standard error of the line as the standard deviation of the residuals, because the residuals, remember, are on average. They tell us how far away something is from the mean. Now, note that we have an n-2 in the denominator. Why is that? Because since we have two variables here, we have an explanatory and a response, the degrees of freedom here is going to be n-2. We have two sets of data instead of one, okay? Now, just keep in mind your calculator is going to give you all of this information. We're just going over where it came from. So in practice, we don't know the population standard deviation for the regression line. So we're going to estimate it with the standard deviation of the residuals. When we estimate the spread of the sampling distribution of B, so remember, okay, so we have all of our slopes in our graph here. The mean is going to be the population slope, and the standard deviation we're going to estimate. Now remember, it's called the standard error of the slope because it's the standard deviation of the sample, the same thing that we've talked about in our previous units, okay? This S right here is the standard deviation of your residuals, okay? This is your standard deviation of your X values, and this is your sample size minus 1. Now, what is the meaning of the standard error of the slope? It estimates how much the slope of the sample regression line varies from the population regression line if we were to do this over and over and over and over and over again. So I have one population slope. I took 100 samples and found 100 slopes. How much do those samples differ from the population slope? So you can think of it as an average of your, are you predicting on average too high or predicting on average too low? Now, what happens if we transform the values of B by standardizing them? So this is the slope. So we're talking about how do we find the, just like we did in our previous questions when we found the z-scores or the t-scores, how do we find the standard values of the slope? Because we're talking about the slope here. Since the sampling distribution of the slope is normal, we can find a z-score here. Now notice what we have, okay? This is still your sample slope minus your population slope divided by the standard deviation of the slope. Not any different than anything else we've done in the past. However, the problem was we don't know the population standard deviation. So what we're gonna do here is we're gonna replace it with the standard deviation or the standard error of the slope, which is the standard deviation of the sample, okay? So you're gonna take your sample slope minus your population slope divided by the standard deviation of your sample or your sample error, okay? Now notice, since we're using a sample standard deviation and not a population, tests about the slope are always going to be t-tests and not z-tests since we don't know the population standard deviation, okay? Now, keep in mind, since we're doing a t-test, you must state the degrees of freedom, which is going to be n-2.